Respected dignitaries, speakers, delegates, ladies and gentlemen, a very good morning and warm welcome to all of you. As we move into the second exciting and vibrating day of ESTIC 2025 and open the plenary session 4, it's time to talk, listen and learn about the ultra-precise timekeeping and quantum control of neutral atoms. The plenary speaker in this session, Professor Hidetoshi Katori from University of Tokyo will be talking to us about the pulsating and emerging area of precision time measurement to space-time engineering. It's my privilege to introduce the session chair, Professor Shankar Kumar Selvaraja, who is Associate Professor at the Center for Nanoscience and Engineering, Indian Institute of Science, Bangalore. Dr. Selvaraja is currently the Project Director of National Quantum Mission, Quantum Computing Thematic Hub at ISC Bangalore. He is the co-founder of Agnit Semiconductors Private Limited, India's first compound semiconductor device startup. A senior member of IEEE and Optica, his research spans photonics, enabled connectivity, computing, and sensing with a growing emphasis on quantum photonic integrated circuits and heterogeneous integration technologies. May I now request the chair, Dr. Selvaraja, to kindly grace the dais and commence the session proceedings, please. Thank you.
So good morning to all here. Thank you for turning in numbers for this early morning session. Very interesting session, I can guarantee you that. And first of all, I would like to thank Professor Katori for accepting our invitation to present his pioneering work on clocks, or rather timekeeping. I'll just give you a brief introduction about the speaker today. Professor Katori is best known for his inventing the optical lattice clock, which is a revolutionary concept that traps neutral atoms in a lattice. And this whole idea, right, eliminates the non-idealities and the noises that you have in the regular system. And this has led to the world's most accurate and stable atomic clock. And this surpasses any traditional way of measuring time. So he is currently professor at the Department of Applied Physics, Graduate School of Engineering, University of Tokyo, and he is the team director at RIKEN, right, where he leads a space-time engineering research program. He received his doctoral degree from University of Tokyo in 1994, and he serves as a research fellow at Max Planck in Germany after that. And he started as an associate professor at the University of Tokyo in 1999. And in 2021, he proposed this idea of clocks. And in 2001, he proposed. And in 2005, in 4 years, he was able to demonstrate this whole concept of optical lattice clocks, which has really enabled a precise measurement and many results in fundamental physics as well. So for his contribution is widely recognized with many awards. I will pick few of those so that you understand the gravity of his work. So he is well renowned with many academic prizes in Japan. A few to notice is Nishina Memorial Prize and Honda Prize, and Honda Prize is considered as an international prize given by in Japan for international scientists, which is considered as a Nobel Prize in technology. And he also received Purple Ribbon Medal of Honor from the Emperor of Japan, and he is also a member of Japanese Academy. Since 2023. With that brief introduction, put your hands together for Professor Katori to hear about clocks. Thank you. Professor Katori.
Thank you very much for a kind introduction. And good morning, everyone. Oh, it is my great honor to speak at this very exciting meeting in a national scale, science and technology and also policy. So today, I will talk about very precise atomic clock. It's so precise, so it will measure the gravitational redshift. It's a relativistic effect. So, the title is From Precision Time Measurement to Space-Time Engineering. I will explain how accurate the clock is, and then we want to discuss how to use this accuracy in the future. This year is the anniversary of the meter convention. 150 years anniversary. So meter convention was signed 1875. And this is the foundation of BIPM, Bureau International des Poids et Mesures. This is the headquarters of international meteorology. To express some quantity, such as length, weight, we use meter or kilogram or second to express time. And these units are according to SI, System International Unité. So, we will talk about the language that science and technology uses. Why we celebrate that legacy, 150 years legacy? We are preparing for the next revolution, which is the redefinition of the unit of second, which is planned in 2030. The spirit of the meter convention dates back to a French Revolution and metric ideal, which is that one law, one weight, one measure. And this spirit of French Revolution is painted by Delacroix, liberty reading the people. So, from the viewpoint of science, I like Manet's Olympia, portraying an ordinary woman, not a goddess, as described by Delacroix. This breaks artistic convention. So criticized at this time, it marked the beginning of modern art. The spirit of developing optical lattice clock is quite similar to this. We have a long history for the atomic clock, and we have convention for making atomic clock. So we want to try another scheme to make more precise atomic clock. This is the idea of developing our clock. So, for celebrating 150 years anniversary, we had a panel discussion how to redefine second at BIPM. In this panel discussion, I talked with Billy Phillips. Billy Phillips is the guy there. And I remembered when I was thinking about the idea of optical lattice clock. It was 30 years ago. I was young, like the young audience in this hall. And at this point, It was early 1990s, so before the GPS navigation. It's quite difficult to trip around Japan for foreign people. So escorting visiting scientists was a privilege for a student. So I was asked to take field trips from Tokyo to Kyoto, where another conference. So during the trip, Bill, this is a Nobel laureate, on the work on his laser cooling of atoms. Bill and his colleague was excitedly discussing that atoms can now be trapped in an optical lattice, like this. This green one is atom, and are trapped by the standing wave of light. This is an extremely new thing, 35 years ago. So it is etched to my mind after 3 hours of trip to Kyoto. An atomic clock using an optical lattice clock tuned to a magic wavelengths came to my mind 10 years later. So this is the very beginning of the research. So before going into detail, I will explain how atomic clocks are familiar to us. It penetrates into our daily life. So Einstein's relativity in 1905, then he said speed of light is constant. In 1983, the meter was defined as the distance that light travels in this time. So one of the applications of such definition is position measurement by GPS. If we observe 4 more GPS satellites, then by measuring the distance between our smartphone and GPS, we can determine our position and also time. We are heavy users of this kind of navigation. So we are already surrounded by very precise atomic clocks. So how do we measure time? So to measure time, we find periodic phenomena such as pendulum or atomic oscillation. Currently, we use cesium atoms oscillation, like that. This is the first thing. Then we count the number of oscillations. Then elapsed time is given by n times the oscillation period. Fluctuation of oscillation period gives a time error. So the position is given by like this. Most stable pendulum gives a most precise clock. This is why we use atom. This is because physicists believe that fundamental constant is constant. And because of that, atomic vibration should be constant and universal. This is physicists' belief. And at the same time, we want to explore if it is true or not. This is another fun for physicists to explore precise atomic clocks. So the accuracy of clock is defined by their pendulum. In this wristwatch, using quartz, if it is a good quartz, it loses 10 seconds in a year. Because of this, we express the precision in this way. 10 seconds divided by 1 year, it gives 10 to the minus 7. Then we say it's a 7-digit accurate clock. Now we use cesium atomic clock, which loses 1 second in 60 million years. Its precision is 5 times 10 to the minus 16. We are talking about optical lattice clock, which is 10 to the minus 18 accuracy. It means which lose less than 1 second over 14 billion years. It's the age of the universe. It's so accurate, so you will wonder how to use this kind of accuracy. So, this is a history of the clock. In the beginning, we observe rotation of the Earth or revolution around the sun. So the work of timekeeping is done by astronomer. Then physicists take over that work. Edison invented cesium clock in 1955. And 1 second is defined by the cesium clock in 1967. Laser technology appeared in 1960. Here. Then, we can develop an optical clock based on a laser, which oscillates much faster than the microwave frequency that drives cesium clock. Important invention in the optical clock is the invention of optical frequency comb, which is done in 1999. Because of this, we can measure optical frequencies very, very precisely. And we dreamed about optical lattice clock in 2001. Then the advance of the research was quite rapid. We observed 1,000 times improvement in 10 years. It's a revolution in clock accuracy. And now we are discussing the redefinition of the second. So, we are measuring the color of fireworks. When you see firework, then we work on this strontium spectrum, which shows purple light. It consists of red-colored light and blue-colored light. We use red-colored light to make clock. The red color oscillates 400 trillion times per second. By counting that oscillation very precisely, and we make a good clock. This is how we do it. We have an atom and shine laser and see the resonance of atomic transition and control the laser frequency to be resonant with the atomic frequency. So we copied the resonant frequency of atom to a laser, which is a macroscopic oscillator. And we divide the frequency. And if you count 400 trillion times 10. We have 1 second. So this is the design of the optical lattice clock we had in mind in 2001. By trapping the atom, green one, in the optical lattice, we freeze the atomic motion. Because of that, there is no Doppler effect when observing atoms. And to have a good signal-to-noise ratio, we collect many atoms in the optical lattice. The important point is that if we trap the atom in this carton-like box, atom got the energy shift in this way. But atomic clock should precisely measure the energy difference between the ground state and the excited state. To compensate this energy shift, we give the same energy shift in the upper state. This is a trick called magic frequency. And thanks to this trick, we designed a very accurate clock. So, we proposed optical lattice clock aiming at good stability and good accuracy. And this background image is our optical lattice clock in the very early stage. We had 50-meter square lab, and optical component and electronics are filled with this whole laboratory space. But anyway, we achieved 10 to the minus 18 uncertainty in 2015. And then we started to make this lab-sized clock transportable and hope to demonstrate relativistic sensing. And we made this kind of transportable clock. Once we make a transportable one, we attempted to lift up one of the clock. This is the clock 1, and this is clock 2. We set the clock at the same height in the beginning, and then we lifted one of the clock to 1 meter above. Then, what will happen? This is it. We measure 2 clocks at the same height for 3 hours. Then lift one of the clock and measure another 3 hours. The clock at the same height shows the same frequency. Then the beat node of the 2 clocks are 0, up to 10 to the minus 18. But if you lift up one of the clock, upper clock ticks faster by 47 millihertz. This is due to the Einstein's general relativity, because gravity slows down the clock. So, on the Earth, lower clock feels more gravity, so it slows down, and upper clock feels less gravity. This is why upper clock ticks faster. So, this is like like Dali's melting clock. Dali, the painter, inspired by the Einstein's relativity and painted this kind of curved clock due to the gravity. So now, this Dali's painting is reality. This is how we are measuring. We can describe 16-digit numbers this way, according to SI. We have upper clock and lower clock, then we get 47 millihertz frequency difference. The important thing is that what we are measuring is indescribable with current SI second. So, in a sense, this is a crisis in science. So, science is that we measure something and according to SI, write down the number in the scientific paper and exchange the data or ideas with the researchers abroad. But we cannot do that scientific work. This motivates the definition of the second. The definition is planned in 2030, and candidate clock or approach will be discussed by 2026. So this is a very interesting timing to think about new second. This is inside the first generation transportable clock using strontium. So we have lasers, colorful lasers, and we have optical setup, which is in free space, and this is a clock itself. We have strontium oven there, and we slow down the strontium by laser cooling technique and cool the atoms at the center of this chamber. This is cooled and trapped atoms by the optical lattice. And we move the atoms into a spectroscopy chamber and measure the clock transition very precisely. I prepared a movie made by RIKEN.
Scientists have done it again. They verified Einstein's theory of general relativity using real-life experiments. The latest group to do it is led by researchers at the RIKEN Center for Advanced Photonics and Cluster for Pioneering Research. And this time, they've done it using a pair of ultra-precise clocks spaced 450 meters apart, one on the ground and the other in the observatory floor of Tokyo's Skytree, one of the tallest towers in the world. Einstein theorized that massive objects warp spacetime, the fabric of existence throughout the universe. One consequence of that is that time runs differently between different gravitational fields, slowly in deep fields and faster in shallow ones. Theoretically, a pair of clocks could capture this time differential. And in real life, that might be easy when the difference in gravitational strength is gigantic. But measuring that difference between two spots on Earth would be practically impossible. That is, if it weren't for optical lattice clocks. An optical lattice clock works by using laser cooling to corral atoms into a well-defined spatial pattern, or lattice. Because the parameters describing this system are so well-defined, scientists can reduce the tiniest disturbances to atomic pendulums. The oscillation of these undisturbed atomic pendulums gives the tick of the optical lattice clock. Clocks of this type were big enough to fill a small room, making it difficult to take measurements at two separate locations. The team, led by RIKEN, overcame that problem by miniaturizing their clocks to fit inside cabinet-sized boxes. Capable of measuring time with 18-digit precision, the clocks produced verifiable differences in the passage of time when separated by 450 meters. And thus, the RIKEN-led team could verify Einstein's theory. But the true innovation is the clock's portability. Small and easy to transport, the clocks could be used to detect otherwise invisible differences in height. That includes foreboding differences in ground swelling in risky areas such as active volcanoes or regions of crustal deformation. In the future, the group plans to deploy hundreds of clocks spaced tens of kilometers apart to monitor the long-term uplift and depression of the ground. The ground networks of optical lattice clocks play a complementary role to the conventional GNSS observation system.
Yeah, it's a good movie. So next challenge for optical lattice clock is that in the short term, application can be chronometric labeling or redefinition of the second. And the relation between the technology and the society is that technology advances first. This is a usual case. And applications transform society later. You will see GPS and GNSS realize such an example. So, as for the social implementation, we made a commercial system in collaboration with Shimazu. And this commercial system will open a new era of timekeeping. I will introduce this thing later. And future challenge is that, like lasers, we want to make the technology into a black box and make this technology accessible to everyone. So optical lattice clocks are evolving into a new infrastructure connecting society and science. So this is how chronometric labeling works. As I demonstrated, if you compare two clocks with a height difference, you will measure this height difference by a gravitational redshift. And if you have 10 to the minus 18 accurate clock, then you can distinguish 1 centimeter height difference on Earth. So you can do a 1 centimeter height mapping using this technique. Now we are working on this direction. This is Japanese island. Tokyo is around here. RIKEN, our institute, is next to Tokyo. In collaboration with telecom company, NTT, we have a fiber connection to north of Japan, which is called Mizusawa. We have an observatory there. And we set our clocks at RIKEN and Mizusawa. One of the reasons we started this project was that we had a big earthquake in this Tohoku area in 2011. At this point, the ground level at Mizusawa subsided 30 centimeters. And now it's uplifting a few centimeters every year. So if we measure clocks over 500 kilometers in this way, we can measure crustal deformation or softness of the Earth by the clock. This is a motivation we started. And another interest we are looking for is a tidal oscillation between 500 kilometers apart. Tidal phase is a bit different. Therefore, we can measure several centimeter height difference every 6 hours. This is our experiment ongoing. If you compare two clocks, clock stability goes down 10 to the minus 18 in about 3 hours. And this is the beat frequency between the clock. And you will see low 10 to the minus 18 level measurement in this way. We are still hunting possible noise, but at least we can measure height difference between the two places at a centimeter uncertainty. And now we are measuring tidal oscillation, which is the blaze of the Earth. So, we started the Mirai project. Mirai means future in Japanese from 2018. It's a collaborative program between academy and industry. In the University of Tokyo and RIKEN, we design ideas for optical lattice clock and develop necessary technologies. And we ask industry, Shimazu, JO, NTT, to make optical lattice clock and commercialize it. In parallel, we have geophysicists and telecom company, and also space agency to discuss how to implement this technology in the future society. And this is inside our clock. We have a 50-liter compact system. You will see outer core strontium atoms emitting a blue light here. This is laser-cooled strontium. By trapping this cold atom into a lattice, we measure clock frequency. So finally, we released the clock from Shimazu and start taking order this March. So it's in Japanese newspaper issued 6 March this year. But one day earlier, there was a AFP report translating this Japanese news. So I was contacted by a German friend for the celebration. It was one day before the Japanese press. So our clock is, this is a price, and it's inside 250 liters. So this is our clock on sale. We have a physics package there, and this is lasers and electronic systems and some other things. In next 5 years, we hope to downsize this system to 250 liter to 100 liter. We have a lot of things to do, but another plan is to extend the lifetime of this system to 10 years. If it is done, we can set this clock on the seafloor or on the moon and across the world. In the long run, 30 liter or palm-sized system is our hope. So, we had a 25 years journey to this product. We have some Japanese fund, and we proposed in the beginning 18-digit accuracy realized, and we started the transportable clock with Shimazu. Now, it's time to harvest the result. The goal is to build a relativistic space-time platform. And space application is one of the frontier. So think about designing the future of time with a seed-driven way. So imagine a palm-sized optical lattice clock in the future. I think it's possible by combining miniaturizing techniques. So such black box clocks will alter our view of space-time. Our mind is still live in an absolute time given by Newton mechanics. If we find two clocks, then we think two clocks should be synchronized. But if you have accurate standalone clock, for example, with 10 to the minus 18 accurate clock, no need to adjust. Clocks lose only 30 picoseconds per year. So, new clock is like this. If you are at the top of the mountain, your clock ticks faster, and at the bottom of the mountain or ground, it's slow. And if your clock is moving, then your clock will be delayed. So the standard clock measure your own proper time. And these comparing clock observe sensor or height difference. And this functions as a sensor for space-time. So, if you have a small clock, and if you go for a drive with that clock, then what will happen? RIKEN is here. We adjust clock to a RIKEN clock and go for drive. If you drive highway at a speed of 100 kilometers, then clock delays. And go to mountain area and climb up to 1,000 meters, then clock advance. And go back to RIKEN again. Then, if you compare your clock and RIKEN's clock, your clock advanced by 600 picoseconds. It means you get older. Or the RIKEN, our calling in RIKEN was a guy in the past. So this shows that we can make a small time trip. So development of clock was a national technology, a national strategy in the past. But who will be the future players? In the era of cesium atomic clock was invented in 1955, and good thing is that US developed a GPS system based on the clock. This is a brilliant US technology to establish an infrastructure of clocks. And they allow to use for they allowed the civilian use in 95, and Google used it, and now we are heavy user of this kind of navigation. And era of automatic drive is now. So think about a similar thing for optical lattice clock. We thought about the idea, and now it's commercialized. And the definition of the second will accelerate the setting up of these clocks. And in 10, 20 years, if you have large number of optical lattice clocks, and if they are connected, then we will think about the relativistic space-time platform business. So we need to think about the strategies for implementing an ensemble of clocks in society. So important thing is to find target that only optical clock can access. We have a huge area that conventional clock is applicable. Because of high performance, optical clock can apply for this purpose. But we need to find this large area that optical clock is mandatory. One of the applications is chronometric leveling. So I was asked to write the final chapter of a high school physics textbook in Japan. The title is Future Shaped by Physics. Here, I wrote about the network of optical lattice clocks, which you'll see what is happening underneath the ground. So this is a last message. Explore freely, shape the future. So we started the work purely curiosity, but it became a clock so precise that won't lose a second in 30 billion years. Then such a clock can see the curved space-time at a human scale. And now it's time to imagine how we use these clocks in future society. Thank you very much for your attention.
Thank you, Professor Katori, for such an interesting talk about time. We always complain about our own time, but you know what are all the things that can happen if everyone is scanning their own time, and no one to complain, right? Because I'm on time always, right? Because I'm on my time. So we have, some time to take a few questions. I'm looking at the right side, Professor Sood.
Thank you very much for this very beautiful and amazing talk. My simple question was, does the time accuracy scale with number of atoms in the lattice? And what is the minimum number you need to claim 10 to the power minus 18? And can it also improve if you go to 10,000?
Thank you very much for a good question. So I skipped this kind of technical details. So number of atoms affect the measurement time. For example, if we have just single atom, then it will take 10 days to achieve 10 to the minus 18 uncertainty. And if you have 10 days is million second, 1 million second. And if you have 10 to the 3,000 atoms, the same measurement can be done in 3 hours. So, number of atoms affect the measurement time to achieve some uncertainty. So, by increasing the number of atoms, you can measure precise time faster. So, we are now making a new technique to speed up our measurement as you expect.
Okay, thank you. Can take one question. I will take two, right? One from NPL director. Can you give the mic here, the front?
Thank you, Professor Katori, for an excellent presentation. I have two questions, two parts. One is the clock-to-clock stability right now. How good is it? And how is it limiting the new definition? And the second one is, though we have the clock stabilities of 10 power minus 18, the clock-to-clock comparison requires communication. That's a limiting channel. So how do we address that?
So, in the lab machine, when we compare two clocks in the lab, then stability goes down mid 10 to the minus 19 in 3 hours. And for a remote comparison, I showed a Mizusawa experiment that connects two clocks over 500 kilometers. In that case, the stability goes down to a few 10 to the minus 18 in 3 hours. So, then as for the accuracy, we evaluate the clock accuracy at the low 10 to the minus 18 level. So currently, to connect two clocks, we have a dedicated fiber, which is stabilized phase. And we are also thinking about the free space link over up to 10 kilometers. And that is another way to communicate two clocks.
All right, thank you, Professor Katori. I know there are many pressing questions and interesting discussion. Professor Katori is available today, rest of today, and also tomorrow. So please, approach him and have the discussion. I have few questions as well, but I have to restrain because we are running out of time. So on behalf of, STEC Organizing Committee and all the participants here, thank you very much, Katori, for the inspiring talk about keeping time.
Thank you very much. It's my pleasure, privilege. Our heartiest thanks to Dr. Katori for taking us into the fascinating world of ultra-precise timekeeping and frequency metrology. I also thank the chair, Dr. Selvaraja, for excellent steering of the proceedings. Lastly, but not at all the least, thanks to the wonderful audience for your support and cooperation. May I now request the session chair to please felicitate the speaker, Dr. Katori, with a memento as a token of our appreciation and step up for a group photo, please. Before we wrap up, there's a small logistic announcement. We are breaking up for tea now. We have to meet again at 11 in the 3 theaters. You have to please refer to the agenda, lecture theater 1, 2, and the plenary at 11. Look at the agenda, choose the choice of your thematics, and kindly be there.
Thank you. Thank you very much. Thank you very much. Thank you very much. What day is this?